Well, my personal connection with durability measurements is my diploma thesis. A good 20 years ago, I had the opportunity to participate in real fatigue strength tests on military helicopters and developed special software to record several hundred strain gauge measuring points. That was a really great and exciting experience as an upcoming engineer, and I'll still like to think back on all the things I was able to learn about strain gauge measurements and operational strength tests from the test engineers and technicians back then. But it is not only in the military that operational strength tests are needed, but above all in the automotive industry. After all, the push for electromobility is changing a lot in the inner workings of new vehicle models, and that's why in the next 25 minutes we want to take a brief look at this very comprehensive topic and deal primarily with the measurement aspects. So today we are going to covering the following questions. Why are durability measurements in electric and hybrid vehicles are so important? How can mechanical measurements such as strains and forces be reliably recorded under high voltage conditions? And how do we combine the measurement data from conventional and high voltage measurement technology in such a way that we can also cleanly perform the calculations that are subsequently necessary, such as the nominal stress analysis? Well, I assume it's not news to you that electric and hybrid vehicles differ significantly from internal combustion engines in terms of their design. The redesign of the powertrain, the large high voltage battery, and the additional electric engines and motors, all of that means that much of that was known before has to be completely re-examined. The roads have remained the same, the impacts, the forces, the accelerations acting on the vehicles remained the same, but in electrified vehicles we have different load distribution, different dynamics, different vehicle mass, different center of gravity, and so on. People are driving differently with electrified vehicles compared to combustion engine vehicles. And the impacts of the road lead to strains, deformations, twisting, stretching, compression of the components, and the components have to withstand that for as long as it is defined. Component suppliers therefore not only make specifications about the maximum permissible accelerations, but also about the maximum deformation of components. So it is therefore important to determine and calculate key figures of fatigue strength. Since some measurements have to be now carried out under high voltage conditions, we need new measurement concepts. So in order to design these measurement concepts, we need to be clear about the objectives of durability measurements. And here are the most important ones. First and foremost, we want to gain a reduction of the mass of a component, because this leads to lower fuel or energy consumption, less material consumption, lower manufacturing costs, more payload, more range, and so on. The second target is to guarantee the function of a component. It must be designed in such a way that the component basically is able to fulfill its purpose. And of course, we want to ensure the safe function of the component over its entire service life, as we define that service life before we construct the component. And naturally, there should be no failures within the service life of a component. And very important in this context is the service life depends essentially on the mechanical loads that affect a component. So what exactly do we mean by mechanical loads? We have a definition here. In engineering mechanics, a load is the sum of all forces affecting a component from the outside. For example, pressure, tension, torsion, and so on. external forces always result in an internal stress on the component or the material used. And those stresses become effective as mechanical tension or compression in the component. And these mechanical stresses reduce the service life of a component. Now let's take a look at a historical example, the railroad accident at Timelkam in Germany. Nearly 150 years ago, this steam locomotive derailed because one of its wheels broke. That was difficult to understand back then because although this wheel was actually designed for and able to withstand the static load, it yet broke. So people began to think about the extent to which smaller but dynamic loads also have an influence on the service life of components. So a German railroad engineer, August Wöhler, started researching fatigue strength, especially for the materials steel and iron. And it was Wöhler who came up with the famous Wöhler lines in fatigue strength, and which we now see here in a generalized figure, generalized because these Wöhler lines are material specific. We now see the stress amplitudes plotted against the load cycle, and this in logarithmic representation. And we can directly see here that there are different areas in these Wöhler lines. It starts at the top left with the tensile strength at 0 load cycles, and then goes through the short-term strength, the long-term strength, and finally the fatigue strength. And what is key here, all loads above the Wöhler line, here, the red area here, lead to the break of the component. Now we are primarily interested in stresses that occur under loads over a longer period of time, as they are carried out, for example, on test benches or above all in road tests. And now the question is how to classify the mechanical loads and their influences on a component, and above all, how do we design a component? How do we configure components? Because depending on the desired application, we pursue different strategies here and accordingly also have different requirements for our materials. Let's take a look at short-term strength. And here's a very practical example of a component which is about to withstand a certain load only a single time. It is a screw with a predetermined break-off head. And this screw is turned into the thread, and finally the hexagonal head is broke off with a single deliberate overload, so that the rest of the screw is virtually countersunk and cannot be removed. An everyday example of short-term strength or operational strength is an iron paperclip. A paperclip is designed to hold a few sheets of paper together, and it does that very well for a long time. But if we bend the clip apart and back together a few times, it breaks. And a good example out of the heart of electromobility is the mating cycles of high voltage safe connectors, which are designed for a specific service life, namely the number of mating cycles. And finally, let's take a look at fatigue strength. Fatigue strength is about designing a component in such a way that it will virtually never break, so to speak, with a still justifiable effort. As an example, we have here a Roman bridge, a bridge from the Roman times, which already has several hundred years under its belt. So we have now roughly defined 3 categories of strength: short-term strength, long-term strength, and fatigue strength. And now we are going to take a look at which requirements for components, that is, which criteria lead to which category a component is to be classified in. First of all, it's about the design specifications of a component, meaning how big should it be, what it is its maximum mass, what appearance and shape should it have, and what material should be used. And here you can see an example of a target design with the requirement lightweight and stable. In the picture here on the left, we see the simulation of a HV battery housing on which already calculated loads have been marked in color here and here, here and here. And on the right, we see a section of the real component where strain gauges have already been applied. And with those strain gauges, we now can measure the real loads, the actual mechanical stress on the surface on the component. And important in this context is a useful overall picture always results only from both calculation and simulation on one hand, and on the other hand, real measurements on the object. The next requirement is the planned use of the component, meaning what real purpose it's intended for a component. And here, let's take a look at an example from the construction industry, namely the pedestrian bridge at the Max-Eid-Lake in Stuttgart. Here, a pedestrian bridge has been designed, which is built for people walking over it and perhaps also bicycles drive over it. And probably it has been determined how many people should walk over it at maximum at the same time, and the designed lifetime for the bridge, usually 60 to 70 years for today's bridges. However, if a car or even a lorry or truck would drive over this bridge a few times, then there would be instantly serious problems with the stability of the bridge there. Another requirement is the stress the user generates, the user of the object or the component. And here we take another example from the automotive industry and look at different customer profiles of automotive users. So here we have, for example, an urban commuter who drives a lot of stop and go, mainly lower speeds with air conditioning and other electrical consumers turned on in the car. Then we have a highway commuter driving longer distances to work and back home with higher speeds and mainly using higher gears. The third one is a leisure athlete who uses a trailer for a boat, for example, most of the time and pulls high loads. Next one is a sports driver who's mostly found on racetracks with the respective stresses that occur there. And we have off-road drivers who bring the vehicle to its mechanical limits. And this last type of user brings us to our next requirement, which is the permitted overload, meaning what degree of abuse, of misuse should a company allow, or must it be able to withstand without causing mechanical failure of the component. Here an example: take a crane that is rented out. Most of its users do not exceed the maximum specified load, but there may be one or two small rebels who intentionally or unintentionally load the crane beyond the specified maximum values. This is then called misuse. Those cases of misuse must also be taken into account and planned for. And finally, we have the requirement of the duration of load and the duration of use of the component. The difference between the two is the duration of use is the gross service life of a component, while the load duration is the true net service life of a component. Let's now take a look at a very specific example from an electric vehicle, namely the operational strength of the housing of a high voltage battery. You see here the high voltage battery, and the objective of the fatigue strength test here is now, number one, that the safety of the battery and the vehicle is guaranteed, and number two, that the housing has a good ratio of robustness and weight. The battery housing is suspended from the vehicle frame at many points, and stresses now occur on the outside of the battery housing when driving, which are caused by twisting of the vehicle frame, and these are indicated here in our example by the red symbols. And mechanical stresses now also occur within the battery. On the one hand, this is due to the external stresses from the vehicle frame, some of which are passed into battery inner parts, but on the other hand, it's also caused by the battery cell themselves. Prismatic battery cells in particular tend to expand during operation, and this is known as swelling. In addition, mechanical stresses also occur at the bus bars here, for example, which connect the cell modules relatively rigidly to one another. And now we want to take a look at how these component loads are determined in practice and what steps are necessary to do this. And this approach looks as follows. We install suitable sensors at precisely defined measuring points inside the high voltage battery and create a measuring point plan, which is a detailed list of all measuring locations and the sensors used there. We will dive on that in a moment. Then we define various test profiles for road tests, defining what loads we use, what speeds are driven, what driving maneuvers are performed, and so on. And in addition, further loads are defined that act on the vehicle from the outside via the test track, for example, whether we simply drive on a level track or whether we have defined bumps or cobblestones or, for example, inclined roadways that are driven on. And of course, we have to think about how we can compare different conditions and circumstances with each other. In other words, how can the data from different test drives be meaningfully compared with each other? For this, we need a suitable concept. So why are we doing all this? What is the goal, the purpose behind all this effort? On the one hand, we want to be able to compare measurement runs. So we want to know, are certain loads similar? Then, and that's very important, we want to be able to make a reliable statement about the mechanical service life of our high voltage battery housing. And in addition, we want to be able to take the measurement data and play it back on a test bench, on the shaker, for example. And on the one hand, we want to be able to repeat certain real situations in a reproducible manner without a road test. And on the other hand, we want to see whether loads from the road test can even be approximately reproduced and compared on the test bench. And finally, we also want to get feedback from our designers and take a look at what are the benefits of design changes to the housing. Do certain changes shorten or lengthen the service life of the battery housing? Well, since today we want to deal primarily with the measurement aspects of fatigue strength investigations, we will look primarily at the topic of installation of sensors and how their values can be recorded in practice. So we now want to know, how do we measure component loads in practice? To do this, we will take a look at the variables, the measurements that are essentially affecting component loads. And these are temperatures, accelerations, and forces. And we have already covered temperatures and accelerations in great detail in past episodes of CSM Explained. You find the videos to those episodes on our CSM Explained archive on our website. So today we will focus entirely on the forces here. Well, all in all, for such investigations, we need values of strain, acceleration, force, displacement, and other operating and secondary measurements. Such secondary measurements are, for example, temperatures, rotational speed, load, speed, loading, GPS data, weather data, everything that helps us to describe the environment and the conditions around the measurement. Now, I just said that today we want to focus on forces, and to determine forces, we usually measure with load cells and pressure cells, or we measure strains in the very classical way with strain gauges. So on the left picture, we now see this typical meandering pattern of a strain gauge, which is the conductor material with a certain material constant, the so-called K factor. And if the strain gauge is now compressed or stretched in horizontal direction from our point of view, the ohmic resistance of the strain gauge simply changes. R becomes smaller or larger. So if you compress the strain gauge, the resistance decreases. If you stretch the strain gauge, the resistance increases. And in order to be able to measure this change in resistance properly, so-called Wheatstone measuring bridges are used. And on the right picture here, we see an applied strain gauge, in our case, one with a strain relieved cable connection pad. And with such strain gauges, we can now measure strain on the outside of the HV battery housing. And for this, of course, we also need a suitable measuring amplifier which supports Wheatstone measuring bridges. So for environments up to 16 volts, CSM offers measurement modules for different bus systems. The upper picture here shows the CAN bus variant, a module providing 6 channels for quarter, half, and full bridges and slower sampling rates. And the picture below shows the EtherCAT-based module, also with 6 channels and fully synchronized acquisition with up to 20 kHz sampling rate per channel. Both variants are very robust. They have protection class IP67 and are therefore suitable both for test benches as well for road tests. And what's also very important, EtherCAT-based modules are synchronized via the built-in distributed clock mechanism, and thus we can create huge decentralized strain gauge measurement networks with several hundred of channels, which are all perfectly synchronized. Think of measuring at giant boom cranes, for example. We have an application note about this on our website, so check it out if you are interested in that. So we simply connect our strain gauge sensors here, the green dots here, to our measuring amplifier via suitable sensor cables, and the data is now digitized here inside the module and can then be sent to a data logger or a measuring computer, for instance. However, if we want to now record mechanical loads or our strain gauges inside the battery, it becomes interesting. Why is that? See, the acquisition of strain gauges under high voltage conditions is of course particularly tricky since we are dealing with strain gauges. They output voltages in the microvolt and millivolt range, but in the high voltage environment we have a potential of several hundred volts, and this is exactly the challenge in electric vehicles when we want to measure strain. So therefore, all non-critical measuring points are usually measured with normal measurement technology, while sensors in the direct high voltage environment must be measured in a correspondingly safe and isolated manner. And for this purpose, high voltage safe measuring systems for strain gauges are required, which consist of a suitable high voltage safe strain gauge cable and of course the appropriate high voltage safe measuring amplifier. And here you can see CSM's suitable measurement module for strain gauges in environments up to 1000 volts. The high voltage SDG4 Pro BS20 is also connected via EtherCAT. It provides quarter, half, and full bridge measurements and up to 20 kilohertz sampling rate per channel. And it's also very robust with protection class IP67. And on top, it offers a lot of additional features for high voltage safety, as we have high voltage safe connectors with mechanical connector routing for the tightness of the connection and band protection. It provides a reinforced insulation up to 1000 volts, and it complies to the EN 61010 standard, which is very common in the entire automotive industry for high voltage test equipment. So with the high voltage SDG module, strains can now also be reliably recorded inside the high voltage battery, for example on the inside of the housing base and the housing walls here. It can also be measured on the dividers between the battery cells and of course on the housing of the cells and the modules. And it can also be measured on the bus bars, for example. And very important, this all is possible with standard strain gauge sensors, which can now be mounted on bus bars despite the high electrical voltages, because our high voltage stem strain gauge measuring module provides the necessary insulation. That means that we now have a solution for strains and forces. However, there were a few more variables that should be recorded for an entire fatigue analysis. So in addition to strain gauge measurements, we can now also acquire accelerations and temperatures with the corresponding high voltage safe measurement modules from our high voltage series, and a corresponding measurement setup could then look like this: the strain gauge signals from the conventional measuring modules, from the strain gauges from the outside of the battery, and the strain gauges inside the high voltage battery can now be recorded simultaneously and synchronously via the EtherCAT bus, that are the green lines here. In addition, the accelerations can be measured on the same measurement bus, the EtherCAT, and as we do not need the temperatures as fast as the strains and accelerations, we have a CAN bus connection, which is sufficient for us here for the temperatures. And these devices are all connected to our data concentrator, the XCP gateway, and then forwarded via XCP on Ethernet to our measuring computer here, or in the vehicle to our data logger. And most likely, we already receive the other operating and secondary measurement as digital signals from the vehicle bus systems anyway, which we can then record at the same time as the analog signals, fully synchronized by utilizing the PTP standard, for example. So we have now clarified which sensors to use where, how to mount them cleanly, and above all, how to read them out, meaning to measure them reliably and precisely. That is what we wanted to show you today. And for further details and questions, you are welcome to contact our experts for discussing your application and requirements. And finally, I would like to give you a few characteristic and guideline values that are important for the recording of the most relevant measurements of fatigue strength. And an important rule of thumb is that the number of channels for typical measurement setup is between about 20 and 100 measurement channels. We will not go through the table in detail now. However, you are welcome to download the complete presentation afterwards in the CSM Xplained archive. There you can also watch the video again later, or recommend the video to interested colleagues maybe who have not the time to participate now here. Well, this brings me to the end of my presentation. I hope that you were able to take away with you today how fatigue tests basically work, what challenges arise under high voltage conditions, and how these challenges can be solved by using appropriate measurement technology. We at CSM have such measurement technology in our product range, both for conventional and high voltage environments, and thus you can get the entire measurement technology for fatigue strength tests from us from a single source. And by the way, for further analysis, for example, according to the nominal stress analysis, we offer open interfaces to software available on the market with our modules. Of course, you are welcome to contact us about this too.